For thousands of years, humanity relied on one primary material to build the foundation of civilization. But hidden inside its incredible success was a catastrophic problem that nobody could solve. If you look at the history of human progress, it is intrinsically tied to the materials we could extract from the earth. We moved from the Stone Age to the Bronze Age, and then to the Iron Age. But throughout all of these technological leaps, timber remained the silent, constant backbone of our infrastructure. The Romans used massive timber frameworks to cast their concrete domes. Ancient Chinese empires built sprawling, multi-story pagodas out of interlocking wooden beams that survived centuries of earthquakes. And the naval fleets that connected the modern world were entirely dependent on the structural integrity of old-growth oak and cedar. Timber was the ultimate building material because it was a naturally occurring composite perfectly engineered by evolution. It possessed a miraculous strength-to-weight ratio, it was relatively easy to machine, and most importantly, it grew straight out of the ground. But here is the problem that architects and engineers began to realize as we moved into the hyper-industrialized modern era. The very biological mechanics that make high-quality timber so incredibly strong also make it impossibly slow to produce. A structurally dense tree, like an old-growth Douglas fir or an oak, requires anywhere from 50 to 150 years to reach the maturity required to yield premium structural beams. For centuries, this timeline was acceptable because human population growth and urbanization moved at a relatively proportional pace to the regenerative cycles of natural forests. But then something changed. The Industrial Revolution triggered an explosion in population and urban density that shattered the equilibrium between what the Earth could grow and what humanity needed to consume. We started building higher, faster, and denser. We needed tens of millions of homes, millions of factories, and thousands of skyscrapers. The biological clock of a forest could no longer keep up with the stopwatch of human ambition. To solve this massive deficit, the answer was not to wait for the trees to grow faster. Instead, we pivoted our entire civilization away from the forest and toward the quarry. We turned to concrete and steel. These materials defined the 20th century, allowing us to conquer gravity and build megalopolises that scraped the sky. Concrete gave us mass and compressive strength, while steel gave us incredible tensile strength and flexibility. But this solution created an entirely new, deeply existential crisis. The production of cement, the binding agent in concrete, is responsible for a staggering 8% of all global carbon dioxide emissions. If the cement industry were a country, it would be the third largest emitter in the world, sitting right behind China and the United States. Steel production is equally devastating, requiring massive amounts of coal to fire blast furnaces to thousands of degrees, stripping the earth of iron ore, and generating billions of tons of greenhouse gases. Furthermore, the sand required for concrete is not just any sand. It must be angular river or marine sand, a resource we are currently exhausting at such an alarming rate that global sand mafias have emerged, literally stealing beaches and destroying aquatic ecosystems to feed the insatiable maw of global construction. We essentially traded a biological bottleneck for an ecological time bomb. We recognize this, and in recent decades, a massive push began to return to timber. The concept of mass timber and cross-laminated timber emerged as the holy grail of sustainable architecture. The idea was simple: grow our buildings, lock up carbon in the walls of our skyscrapers, and stop burning fossil fuels to make steel. But the twist most people miss is that the mathematics of modern mass timber do not scale to a global level without devastating consequences. To build the future out of traditional wood, we would need to harvest billions of trees. To keep up with demand, the timber industry relies on fast-growing softwoods like pine and spruce, which can be harvested in 20 to 30 years. However, these fast-growing softwoods are inherently less dense and structurally weaker than old-growth hardwoods. We are caught in an inescapable paradox. The wood that is strong enough takes a century to grow, and the wood that grows fast enough is not strong enough to replace steel on a massive global scale. This is where things get interesting, and where an overlooked alternative steps out of the shadows. What if there was a biological material that possessed the rapid growth cycle of a weed, but could be engineered to possess the structural integrity of industrial steel? For decades, engineers searched for a synthetic solution: carbon fibers, advanced polymers, complex resins. But these were astronomically expensive, and relied on the very petrochemical industries we were trying to escape? The answer was not engineered in a laboratory. It had been growing in the tropical and subtropical belts of the planet for millions of years. The material is bamboo. Now, pause for a second, because when you hear bamboo, your mind immediately jumps to the wrong image. You picture hollow, green tubes used for decorative garden fences, tiki torches, or perhaps the precarious but impressive scaffolding you see strapped to the sides of buildings in Hong Kong. You think of a material that splits easily, rots when exposed to moisture, and is entirely hollow on the inside. How could a hollow piece of grass possibly replace a solid steel I-beam or a massive structural timber column? That skepticism is exactly why bamboo was ignored by Western structural engineers for over a century. Bamboo is technically a perennial evergreen grass, not a tree. Because it is a grass, it does not grow by adding concentric rings of wood year after year like an oak or a pine. Instead, it pushes out of the ground at its full diameter and simply telescopes upward, driven by a biological mechanism that makes it one of the fastest-growing organisms on planet Earth. Certain species of running bamboo can grow up to 35 inches in a single 24-hour period. You can literally watch it grow. Within 4 to 5 years, a bamboo culm reaches its absolute peak structural maturity, at which point its cellular walls are packed with dense lignin and cellulose fibers. This growth cycle is 10 times faster than the fastest commercial softwoods, but the fundamental problem remained. A hollow tube, no matter how strong its outer wall, cannot be easily standardized. You cannot seamlessly bolt it together to build a towering office building. It limits architectural geometry, and it is highly susceptible to insect attacks because it is full of natural sugars and starches. The breakthrough came when materials scientists and engineers in China decided to stop treating bamboo like wood and started treating it like a raw chemical ingredient. They realized that the magic of bamboo was not in its tubular shape, but in its microscopic cellular architecture. Bamboo fibers, pound for pound, have a higher tensile strength than many alloys of steel. The challenge was figuring out how to extract that microscopic strength and reconfigure it into a macro-scale solid geometry. This led to the development of a revolutionary material known as bamboo scrimber, or engineered structural bamboo. The process of creating this material is nothing short of an industrial metamorphosis. It begins in the massive bamboo forests of southern China, where the grass is harvested at precisely the 4 to 5 year mark, ensuring the perfect ratio of flexibility to hardness. The hollow culms are brought to a processing facility, where they are split horizontally and run through massive mechanical crushers. But these machines do not pulverize the bamboo into dust. Instead, they carefully crush the culms to break down the rigid outer walls while keeping the long, vertical cellulose fibers completely intact. What you are left with is a loosely connected, highly porous mat of raw, fibrous grass. Step back and look at the bigger picture here. Engineers essentially unzipped the hollow tube and flattened it into a continuous web of superfibers. But these fibers are still full of natural sugars, which are an open invitation to termites, beetles, and fungal rot. So the raw fiber mats are submerged in massive boiling vats. Through a highly controlled process of hydrothermal treatment, the starches and sugars are entirely stripped away, leaving behind pure, unadulterated structural fiber. This boiling process also fundamentally alters the chemical composition of the remaining lignin, making the fibers more stable and less prone to expanding or contracting with humidity. Once the fibers are dried to a precise moisture content, the true alchemy begins. The dried fiber mats are submerged in specialized vats of phenolic resin, a highly durable, water-resistant adhesive binder. Because the crushing process made the fibers incredibly porous, the resin penetrates at a deep cellular level, coating every single microscopic strand of cellulose. The resin-soaked mats are then layered into massive steel molds. This is where the magic happens. Giant hydraulic presses slam down on the molds, applying thousands of tons of crushing pressure, while simultaneously blasting the material with intense heat. This process forces the separated fibers to compress and interlock at a density far greater than any natural wood could ever achieve, while the heat causes the phenolic resin to undergo a chemical cross-linking reaction, curing the entire mass into a single, unified, indestructible block. The result of this extreme heat and pressure is a completely new category of material. When the block is ejected from the press, It no longer looks or acts like grass. It is a solid, incredibly heavy, dark amber timber. It is so dense that it sinks in water. When engineers tested this new engineered bamboo, the numbers were staggering. Its density is over 1.2 grams per cubic centimeter, making it significantly harder than oak, teak, or mahogany. Its dimensional stability is extraordinary. It does not warp, twist, or split when exposed to extreme weather variations. It is highly fire retardant because it is so dense that oxygen cannot penetrate its surface to feed a flame, meaning it chars slowly rather than bursting into fire. But most importantly, its modulus of elasticity and tensile strength are off the charts. It can bear loads that would snap traditional mass timber in half, and in specific applications, it rivals the load-bearing capacity of concrete and mild steel, but at a fraction of the carbon footprint. Most people overlook the material, but the numbers do not lie. Real projects prove it works, and this is where the theoretical engineering translates into spectacular physical reality. China did not just invent this material and leave it in a laboratory. They have rapidly scaled it into a cornerstone of their future infrastructure. The Ministry of Housing and Urban-Rural Development recognized that China possesses some of the largest bamboo reserves on the planet, and they have actively pushed policies to replace steel and plastic with engineered bamboo. If you travel to the infrastructure hubs of modern China, you will see this material performing tasks that seem impossible for a grass. Engineers are laying down massive underground municipal water pipes made entirely of bamboo winding composite technology. By wrapping resin-soaked bamboo fibers around a mandrel, they create high-pressure pipes that are lighter than steel, immune to rust, more durable than PVC, and capable of withstanding the immense crushing weight of city traffic above them. But they didn't stop at pipes. The transportation sector has aggressively adopted the material. Inside the carriages of China's sprawling high-speed rail network, trains that hurtle across the country at hundreds of kilometers per hour, the flooring and structural paneling are increasingly being replaced by bamboo composites. The material absorbs vibration beautifully, dampens sound, and significantly reduces the overall weight of the train, which translates directly into massive energy savings over the lifespan of the vehicle. Stepping outside the cities, rural infrastructure is being entirely reimagined. Engineers are constructing massive highway bridges where the primary load-bearing arches and girders are manufactured from giant sweeping curves of laminated bamboo. These structures can support the weight of heavy commercial logging trucks and shipping containers, proving their resilience under immense dynamic loads. In the renewable energy sector, the innovation reaches even greater heights. Wind turbine blades, which are traditionally manufactured from unrecyclable fiberglass and epoxy resins that end up rotting in landfills, are now being prototyped and manufactured using engineered bamboo composites. The bamboo provides the incredible stiffness and aerodynamic flexibility required to catch the wind, while drastically reducing the environmental toxicity of the blade's eventual disposal. The material is stronger than expected. A manufacturing breakthrough changed everything, and it is scaling at a pace that is leaving traditional material scientists stunned. To understand why this matters on a civilization scale, you have to look at the geopolitical and environmental map of the world. The bamboo belt wraps completely around the globe, spanning across Asia, sub-Saharan Africa, and Central and South America. These regions correspond heavily with the global South nations that are currently undergoing the most rapid and massive urbanization in human history. Historically, to build their developing megacities, these nations have been forced to import wildly expensive steel or rely on highly polluting domestic concrete production. But engineered structural bamboo offers a radical alternative. It provides developing economies with the ability to literally grow their own advanced structural materials in their own backyards. A country with minimal iron ore reserves but ample tropical climate can cultivate millions of acres of structural bamboo, harvesting it every 5 years in a continuous, perpetual, and sustainable loop. It completely shifts the power dynamics of resource dependency. Instead of mining finite resources out of the earth and leaving behind toxic scars, we could be managing high-yield, hyper-fast-growing agricultural forests that actively pull millions of tons of carbon dioxide out of the atmosphere. The bamboo plants sequester carbon as they grow, and when the grass is harvested and locked into a high-density structural beam for a skyscraper, that carbon is permanently trapped inside the building. The skyscraper transforms from a carbon-emitting liability into a massive, functioning carbon sink. It is one of the few industrial processes that is genuinely climate positive rather than just less bad. However, to view this purely through a lens of unbridled optimism would be intellectually dishonest. Every major technological leap comes with its own friction, and this material has critical limitations that engineers are currently battling to overcome. The most pressing issue lies in the adhesive binders. While the bamboo itself is perfectly natural and sustainable, the phenolic resins used to bind the fibers under pressure are highly refined petrochemical derivatives. They require fossil fuels to produce, and if not manufactured, with extreme precision, they can off-gas formaldehyde and other volatile organic compounds. The industry is racing to develop bio-based resins, adhesives derived from soy, lignin, or other plant-based proteins that can withstand the extreme heat and pressure of the scrimber process without compromising the structural integrity of the final beam. The breakthrough in bioresins is the final missing piece of the puzzle to make engineered bamboo a 100% ecologically pure material. The second major limitation is the immense energy required for the manufacturing process. Crushing, boiling, drying, and hydraulic pressing at thousands of tons of pressure demands massive amounts of electricity. If a factory producing engineered bamboo is powered by a coal-fired grid, the carbon math starts to heavily degrade. The true environmental potential of this material can only be unlocked if the manufacturing hubs are powered by renewable energy, solar, wind, or hydro. Furthermore, there is the massive bureaucratic wall of global building codes. In North America and Europe, structural engineering codes are written almost exclusively for steel, concrete, and traditional softwood timber. There are incredibly rigid, highly specific testing parameters for how a pine 2x4 performs in a fire or a seismic event. Engineered bamboo is so new, and its properties are so different from traditional wood, that Western regulatory bodies simply do not know how to classify it. An architect in London or New York might desperately want to design a 20-story high-rise using bamboo structural columns, but they are often blocked by local zoning laws and building inspectors who lack the standardized grading metrics to legally approve the material for commercial load-bearing use. Changing international building codes is a glacial process, often requiring decades of repetitive lobbying, controlled demolition testing, and bureaucratic wrangling. Yet, despite these hurdles, the momentum is undeniably building. We are standing on the precipice of a fundamental shift in how we conceive of the built environment. For a century, we believed that the only way to build strong was to build heavy, to extract, to mine, and to melt. We viewed biological materials as archaic relics of a pre-industrial past. But the twist in the narrative of human engineering is that nature had already solved the problem of strength, flexibility, and rapid regeneration at a microscopic level. It just took human ingenuity, immense pressure, and a willingness to look past the obvious to unlock it. The buildings of the next century may not be poured from liquid rock or forged in blast furnaces. They may be planted, harvested, crushed, and pressed into existence. We are moving toward an era where the towering skylines of our greatest cities are quite literally grown from grass. Think about this the next time you see a concrete high-rise going up in your city. What other overlooked technology, hiding in plain sight, do you think could completely change the world?